The main hypothesis of the paper is that fish utilize a special mechanism involving the swim bladder and inner ear structures to achieve directional hearing underwater. Previous theories involved investigations into sensory systems like the lateral line system. However, they were limited in their ability to account for processing of higher frequency sounds and the ability to determine sound direction effectively. The paper proposes that the swim bladder functions as a pressure displacement transducer, converting sound pressure waves into mechanical vibrations and then transmitting these vibrations to the inner ear, enabling the fish to perceive direction of sound based on differences in amplitude between its ear and face. The paper uses several key methods to investigate the proposed hypothesis using anatomical studies, behavioral experiments, and computational modeling. Anatomical studies were used to identify structures that may facilitate sound transmission and their mechanisms, while behavioral methods were used to expose fish to sound from different directions and record their responses to understand how fish perceive sound direction. These were performed in Danionella cerebrum, which come with the limitation of not necessarily being generalizable to all fish in all cases, however provide a good baseline. Computational methods were used to simulate how sound waves interact with the swim bladder and inner ear system, allowing for mathematical analysis of how these interactions lead to directional hearing. The computational model assumes that the swim bladder operates as an efficient receiver of sound waves, and that the transmission of these vibrations to the inner ear is lossless and direct. An engineered system which could model these conditions involves a pressure sensor replacing the swim bladder, a particle motion sensor array replacing the inner ear, a microcontroller, and filtering methods. The pressure sensor can be used to detect oscillating sound waves, while the particle motion sensor can be used to capture the movement of particles in the medium. Pairing the two of them together, we then take the relative phase and the envelope of the signals to determine directionality of the sound source. The data is also filtered, as in the real world, systems will have a lot more noise than in computational experiments. The system can be designed to estimate the distance of the sound source by implementing time-of-flight measurements. By introducing a timing mechanism between the speaker and the pressure sensor, we can record the delay between the emission of the sound and arrival at the sensor. By multiplying the value of the speed of sound in the medium we're using, we can acquire a distance. It's also possible to measure distance using attenuation.